Hello everyone, and thank you for joining me today in this lesson about solving radical equations. We have two objectives today. We are going to solve radical equations, and we're going to practice identifying extraneous solutions. As you may have guessed, a radical equation is an equation that has a radical expression in it. The cubed root of x squared plus 4 minus 2 equals 0 is one such example. Admittedly very blurry, but that is an example of a radical equation. We solve these equations much like solving other equations. We use inverse operations to peel away at the layers of this equation before we can get to that variable inside. Something to keep track of, though, is that when we go to cancel out the radical, we want to make sure we have that radical isolated first. For instance, in this example, if a person tried canceling out this cubed root by cubing both sides right away, that will make a huge mess because of this minus 2. With that being there, we'd actually have to multiply this out 3 times, which will make a huge mess. But if we can make that go away and bring it over here, like this person did, then that cube root is just going to cancel with that cubing exponent, and we'll have just that x squared plus 4 left. So we really do want to isolate the radical before we do anything to cancel that radical out. Once we do cancel that radical out, we'll go ahead and solve what's left. That might be a 1 or 2 step linear equation. That might be a quadratic equation that needs to be factored. We'll see examples of both today. In some situations, when we say square both sides to cancel out a square root, we create some extra solutions that don't work in the original, and those are called extraneous solutions. So we'll keep an eye out for those today as well. To keep this video brief, I'm cutting a few examples here. We'll do a total of 3 that range from perhaps less complicated to more complicated. So we'll start here. We're going to solve this square root equation, and we may check for extraneous solutions as well. Once again, we want to isolate the square root before we try to cancel it out. If we were to square both sides right now, that would be very messy because we'd have to FOIL this times itself, which will make things harder than we want them to be. So let's take a few algebra steps to isolate that square root instead by adding 1 to both sides and then dividing by 4 on both sides. Now that we have that radical isolated, we'll get this perfect canceling action when we square both sides, giving us a final answer of x equals 1. We can plug that back in to check. We could also check graphically using techniques we've discussed in the past. I can tell you that this equation does not have the right stuff to create those extraneous solutions. And we'll look at an example next of an equation that does. Again, the big idea is to isolate that radical before you cancel it out. And here we had canceled out a square root by squaring both sides because those are inverse operations. What makes this equation now different is we now have a variable inside and outside of a radical expression. And this situation right here is where we really have a chance to create these extraneous solutions. So we'll make sure that we check for them here. We also are going to have a little bit more of a challenge here algebraically, because when we do square both sides, we'll create something that's a little bit harder to solve. And we'll see that when we get there. But first things first, we still want to isolate the radical if necessary, and it already is isolated. There's nothing else over there that's going to make a mess of things. So we're ready to go ahead and cancel out that square root by squaring both sides. And notice that we don't actually square what's in here because that exponent's just going to cancel out with the radical there. So we leave the 2 minus x. That's what we have over on that left-hand side. On this right-hand side, when we square x minus 2, we've got to do that correctly, which is to FOIL x minus 2 times itself. And I will spare you the details there. But this time we're left with a quadratic equation that needs solving, instead of just a 2-step or even 1-step linear equation like on the last slide. And our techniques for solving quadratics in order are typically factoring and quadratic formula, but both of those techniques require our equation to equal 0. So we have to move all the terms over before we can start either of those techniques. And for my money, I'm going to move these over to the right to make sure my quadratic term is positive. Just easier for me to factor when I do that. So when I add this x over, I'll then have a minus 3x. And when I subtract this 2 over, I'll then have a plus 2. So now I'm going to try factoring this quadratic trinomial. And the quadratic formula would work too, but if something's factorable, it's often faster to do that. So we're thinking of numbers that multiply to 2 and add up to -3, and those numbers are -2 and -1. With those as our factors, our solutions then would be positive 2 and positive 1. I made a big deal about how this is a situation where we might create some extraneous solutions. So before I put a box around those, I'm going to double check both of them. And the key is that I check them back in this original equation before I squared both sides. So switching colors here, the first thing I'm going to check is x equals 2. So going back to that original equation, we had square root of 2 minus x on this side, and I'm plugging 2 in for x. Sorry, I won't give you motion sickness here. On the right-hand side, we had x minus 2, so 2 minus 2 in this case, where we end up with the square root of 0 equaling 0, and that's a true statement. So x equals 2 works just fine. Let's check x equals 1. So taking the original equation, plugging 1 in for x now. I'll zoom out one time here. We'll have square root of 2 minus 1 on the left, and on the right-hand side, we'll have 1 minus 2 when we plug 1 in for x. And on this left-hand side, we get square root 1, and on the right-hand side, we get negative 1, and that is not a true statement. The square root of 1 equals positive 1, and that shows me that x equals 1 is one of these extraneous solutions, and so x equals 2 is the only valid solution we have here. You could also confirm that graphically by graphing the left-hand side, the right-hand side, and finding where they intersect. You'll find the only point where they intersect has an x-coordinate of positive 2. So we've seen two examples so far. The first was on the less complicated end. The last one was more complicated because we had to solve by factoring and check for extraneous solutions. This last example may not be any more complicated than that, but it looks a little bit different to start off with. So recently, we talked about rational exponents and how rational exponents are another way for us to write radical expressions. So although this doesn't look like a radical expression right away, perhaps, it truly is one in disguise because this expression I just highlighted is really a radical expression. Now we kind of have two different approaches to how we go about solving this, but either way the first step is still to isolate that radical expression, which means we're going to want to divide by 3 on both sides. So then we'll have x plus 1 to the power of 2/3 equaling 4. And from here we kind of have two choices. So I'm going to go kind of two branches here. Option number 1 I'm going to do in red, and in this option here we're going to take x plus 1 to the power of 2/3 and we're going to rewrite it as a radical. And remember, the top number in this rational exponent tells us what the power is for x plus 1, and the bottom number 3 tells us what type of root we're dealing with. So when I go to rewrite this as a radical expression, we will have the cubed root of x plus 1 squared. That is equal to 4. The benefit to doing this way is that now we can treat this the same as our other, examples using the same strategy. We already isolated the radical. Now we're going to cancel out the radical using an exponent, and then we'll solve what's left. Well, here the exponent we're going to use is a 3. We've got to cancel out a cubed root this time. So we'll cube both sides. And then we'll have just the stuff left inside of that cube root on the left, and on the right, 4 cubed is 64. Well, now we've got to solve what's left. And we could take x plus 1 and actually square it and FOIL it out, but really I think this is a great place to use a square root just to cancel out that exponent. But then here's the twist on this. That's all well and good, but we got to remember that when we solve using square roots here, we would have plus or minus 8 on that right-hand side for the square root of 64. So really we're going to get two solutions here. Either x plus 1 equals positive 8 or x plus 1 equals negative 8. And when we subtract 1 from both sides here, these are the two possibilities we'll get. We could check them, plug them both back in, we'll find that neither of them is extraneous. They both work just fine. That's option number 1. Here's option number 2. I'm going to do this in green. We had x plus 1 to the power of 2/3, and that was equal to 4. Instead of rewriting this as a radical, what we could do is we could cancel out this exponent by using an exponent that's a little bit different. And the exponent that we would use here is the reciprocal of the power we started with. So x plus 1 was being raised to the power of 2/3. We're going to raise both sides to the power of 3/2, because when we multiply these together, which is what we would do in this situation, they equal 1 as a product, which means they cancel each other out. So on this left-hand side, then, we just have x plus 1, and on the right-hand side, we have to do 4 to the power of 3/2. This is where things get a little bit tricky, because we know 4 cubed is 64. Let's see here. Nope, I didn't do that right. I didn't write that down right. I got to go back. My fault. Sorry about that. Let's talk about just maybe doing this on a calculator, right, to speed things up a little bit. And we could rewrite this as the square root of 4, then being cubed. But the whole point is to go faster here. So let's say you do this on a calculator, and you will end up getting 8 here, which isn't maybe a surprise because that's what we got over here. But this is where you've got to be careful. You have to recognize that what this exponent is doing is it's cubing 4, but then taking the square root of that. Just like exactly what we did over here. We cubed both sides, then we took the square root of both sides. But the kicker is that when we take that square root, we've got to remember that plus or minus. And that's a little bit harder to see perhaps when you don't physically have that square root in front of you like we have in pink over there. So while this technique might be a little bit faster, it's perhaps a little bit more risky in a situation like this, because you might miss that square root leading to this plus or minus symbol here. And if you're able to manage that and you can remember that, then this is just fine. But if you find that you might forget that or miss that, you may want to go this route, where you rewrite that expression as a radical, and then you can see it all play out in front of you there. So 2 choices there. You find one that works best for you. We kind of breezed through that, and I cut a little bit of content. You can find some completed notes perhaps to fill in some of the gaps that I chose to skip over there. But for now, that's enough about solving radical equations. Thank you for watching.